Welcome to my talk on temporally discounted differential privacy for evolving datasets on an infinite horizon. This work was conducted while I was still at CSIRO's Data 61, but since then I have moved to the University of Melbourne. This paper is partially funded by the NEAR project. The NEAR project is a big project between the Australian government, especially Department of Environment and Energy, CSIRO and AMO on forecasting energy consumption in Australia in the future. And being able to attend this conference and presenting this paper is funded by the Melbourne School of Engineering. Being able to ensure differential privacy for evolving datasets, especially on an infinite horizon, is a very difficult task. And that comes back to the composition theorem, a fundamental property of differential privacy. The composition theorem says that the privacy budgets for each report add up to construct the privacy budget for the entire report, the overall privacy budget, as we report more and more based on a given private dataset. So as time goes on, the overall privacy budget will scale linearly with the number of the reports that you have done. Now, better bonds have been presented for other notions of differential privacy, such as epsilon delta differential privacy. But the big thing here is that no matter what people have done so far, the best rate of growth for the overall privacy budget and for some queries has been logarithmic in the number of the reports. And it has been even shown that for some queries, it might not even be possible to ensure overall privacy budget with a fixed, constant budget with a finite magnitude additive noise. Now, let's get some notations done to be able to present what is discounted differential privacy. Differential privacy and privacy loss, we have to first define them. To get there, we have to define the dynamic datasets or evolving datasets, xt, and each row of it is the data of an individual, a given household, for instance, and the smart meter measurements of them goes into the row of each house. Each column is the new measurements that we get at a given time. So as we go on, this matrix will get larger and larger. Now, at each time instance, we report a y, yt for instance here, based on the whatever has been in the datasets so far. Now, this could be a function of the measurements of the current time or the previous time. We are not restricting ourselves. Now, differential privacy requires us to be able to ensure that the statistics of the output yt, capital YT here, does not change much if we are changing the data of a given individual. So changing the data of a given individual creates this concept of neighboring datasets. Two datasets are neighboring with each other if we only change the data of an individual. Now we look at the probability of observing an output given one of these datasets and the probability of observing the same output given a neighboring datasets. Now the likelihood ratio of them should be bounded by epsilon, which is your privacy budget, your overall privacy budget. Now if we have causality in the way that we report, i.e. if each yt is only a function of data that he has previously observed up to that time t, and if we have independence of the noise when we are generating this yt, so the noise that we are using for generating yt to ensure privacy is independent of the noise that we are using for generating yt, not the underlying dataset, but the noise of them, then we can expand this condition for differential privacy into a sum. Each term of this sum is the privacy loss. Privacy loss at the first step, privacy loss at the second step, up to privacy loss at the t step. Now, if we sum up all these privacy losses, they should be bounded by the overall privacy budget. Now you see what's the problem here. If each privacy loss is kept below a constant, the sum of them might go to infinity. So to be able to ensure this condition for any t, not for a given horizon that we are thinking about, we don't want to halt our reporting tomorrow, the day after, or a year from now. We want to just go on reporting forever. This condition should be guaranteed for any t. That means that as we go on by reporting more and more, we should let the privacy losses to go to zero. Now, pushing the privacy losses towards zero means adding more and more noise to each report that we are releasing. So that report becomes less useful as time goes on. Why discounting the losses? Well, discounting losses is a popular thing in economics, and it's often motivated by two factors, either by cash and interest rates or by self-control in rational agents. Now, cash and interest rates notes the fact that, if you have money in the bank, it's going to accumulate interest as time goes on, or because of inflation, if you have money in your pocket, you're going to lose more money as time goes on. So the way that you are balancing the losses at the current time and the losses in the future, or the gains in the future or in the past, would be a function of these interest rates or inflation rates. For instance, in the context of privacy, you can think of it if you're a big company and have put money aside in a fixed account, and you're putting that money aside for answering all the legal obligations that might come with the private information leakage of your customers. So if you're going to get fined in the future because of GDPR or similar frameworks, then you put the money aside, and this money is gathering interest over time. So the way that you think about the loss over time is going to change, possibly, because you have more and more money in this fixed account without even doing anything about it. In addition, self-control in rational agents has shown that the way that we think about loss over time changes, and that's because of a self-control. We would like to do things now rather than wait for them in the future, or if they have happened in the very long distant past, we don't tend to care about them that much, and our memories of them fade away. So that would mean that the way that we are kind of balancing all these losses and gains over past and future would change over time. It's interesting because privacy and self-control are related to each other. The way that we think about privacy is highly related to the way that we think about self-control. It's a self-control mechanism not to look in our Facebook or put, check-ins of private information there. So you can think about the very fundamental relationship between self-control and privacy there. So if we have some kind of results when it comes to self-control in rational agents, they would probably extend into privacy as well. Now, in the context of privacy, there is one more reason even to discount losses. Data gets old very fast. If we have the data about a bunch of houses at a given time, 10 years from now, they are not going to be as important because most of the people who live in these houses have moved on. And that kind of shows itself in the way that companies look around and try to gather the most recent data and the most high quality data. Nobody is interested in looking in the very, very old data sets unless we have a reason that not much has changed within these data sets. Temporal discounting is interestingly conjectured to be a reason as why individuals don't do much when it comes to protecting the private information. Now, to understand this, we got to try to separate the concept of privacy attitude and privacy behavior. Privacy behavior is what we actually do when it comes to protecting our private information, while privacy attitude is what we think we should do or other people should do when it comes to private data. We might think very much about how Facebook is, intrusive about our privacy and how it's, we are sharing a lot of data with other people and we shouldn't do it. But when it comes to actually implementing those things, we might not be on the same page. And that's because of the difference between privacy behavior and privacy attitudes. Now, the discounting is not going to change our privacy attitudes. We are going to still think about the fact that, some of these services are intrusive and we shouldn't share as much information and other sort of things, while it is important in the way that we're trying to answer this kind of privacy, control questions. How do we, balance the fact that we want some services currently at the given time right now and don't want to wait for them in the future, or wait for them when they are a bit more, or do them more inconveniently, while we want to balance that with our privacy. So certainly, discounting would fit more into the privacy behavior rather than a privacy attitude. Now, what is discounting privacy? So think about that big sum that we got, which was the definition of a differential privacy expanded to all the losses being summed up, being bounded by epsilon, which was your overall privacy budget. Now, in exponentially discounting, we essentially discount each privacy loss based on the time since the current report that we did. Okay, so if that report was in a very, very long time ago, then we are discounting it by a very, very small coefficient. And that would mean we care about it not that much. So to be able to satisfy this sum, our life gets easier. Now again, exponential discounting dates back to the early 20th century as it's mainly motivated by the interest or the cash rates. To be able to ensure this new notion of privacy, which is the exponentially discounted differential privacy, we can use the same kind of mechanism that are there for differential privacy. A big mechanism there is Laplace noise. So people add Laplace noise and they select a scale of the noise based on the sensitivity of your query over the privacy budget. Now, what we do here that instead of having one query, we have a lot of different queries, each for a given time. Now we look at the sensitivity of each queries, defined in a very similar way as we define the sensitivity of a query in differential privacy, by changing only the data of one individual. So looking at the neighboring datasets and looking at the sensitivity or the changes of this query at the given times. Now we select an upper bound for the sensitivities across time. And we use this as to find the scale of the noise that we add for ensuring discounted differential privacy. So we have again, very similar to before, we have sensitivity or epsilon. Now we have another factor here, 1 minus delta, which shows the effect of the discounting. So if we don't discount much, if delta is very close to 1, then you would see that the amount of the noise would become very large. But if delta is very close to 0, it's very small, so we're discounting heavily as we go on, the effect of it on the noise would be much less. Interestingly, here you can see that we can attain a fixed magnitude for the noise. We don't need to increase the amount of the noise to be able to ensure this notion of discounted differential privacy. Another way of discounting privacy across time is hyperbolic. Now, why would we select hyperbolic discounting? It's because of studies out there that show that humans, animals tend to often do the hyperbolic discounting when it comes to their decision making. And that's kind of motivated by self-control. So if we try to relate privacy and discounting together through the self-control, then it might be a better way to discount losses across time by a hyperbolic function. And that's essentially showed itself as this rational function here. So instead of having an exponential, we have this rational function that's linear in the time since the current report. And the beta is your discounting factor. Here, when the beta grows larger and larger, you would have a higher discounting factor. And when beta is smaller, you would have a smaller discounting factor. Now again, you can show that Laplace noise would be able to ensure hyperbolically discounted differential privacy, while there is a caveat here, that the fact that the amount of the noise would have to be increased with time. So the more that you report and you go forward, you have to increase the amount of the noise, which is not something good. And in fact, this scale that we have observed here is the square root of the number of reports so far, which is quite high. But at the same time, we got to note that this is not we are not saying this is an optimal mechanism. So it might be possible to find better mechanisms that would have a smaller increase, and that is sensible, because if we can ensure differential privacy with logarithmic increases in the amount of the noise, we should be able to do hyperbolic discounting too, because if we can meet the hyperbolic discounted differential privacy, we can meet the differential privacy too. So the same kind of mechanism should work here too, to be able to ensure hyperbolically discounted differential privacy. So with the discounting, we should even get better than logarithms. So one avenue for future work is to try to look into these optimal mechanisms when it comes to the growth of the noise across time. Now let's look into a numerical example and see the effect of the mechanisms that we have introduced and the effect of the discounted differential privacy. We use the Ausgrid data. Ausgrid is a company in Australia, and it has released 300 anonymous Australian houses measurements, smart meter measurements on a 30-minute windows over 3 years. These houses have batteries, solar panels, movable appliances, schedulable appliances and stuff. And although this data is publicly available, we have made sure to obtain ethics approval to be able to use this data and show this aggregated information to you and the effect of the algorithms and the policies that we introduce in the paper. Now, let's look at a very simple case that we are trying to report the average consumption across these 300 households. Okay, and we can find easily the the sensitivity of function, because the function is linear and it's an averaging function, and we can set the privacy budget to 1, because it wouldn't, everything would get scaled by epsilon anyhow. So let's just, for the sake of presentation, set that to 1. Now we can look at the trade-off between utility and privacy. So if we have a low amount of discounting, so if we don't discount at all, we would be differential private. If we have low amount of discounting, we would be very close to differential privacy. And as we discount more and more, we would get further from differential privacy. So our privacy guarantees gets a bit weaker overall. So when we are using a very large delta, close to 1, we are very close to differential privacy. And as you can see here, when we are reporting this many measurements over 1 year with 30-minute windows, the amount of the noise that we require to be able to ensure that is quite large. So that might not be as good of a utility. So that would be a very bad utility for a very high privacy. Now, as we decrease the delta, we would be discounting stuff that has happened in the past more and more, and the effect of it shows itself here in the amount of the noise that we are adding here, because the amount of the noise that we are adding here gets smaller and smaller. So when we are getting towards the discounting factor of 0, effectively the amount of the noise that we are adding is negligible, and that is and we are getting very close to the true average consumption reports. Now, in the beta case, in the case of hyperbolic discounting, as we increase the beta, means we are discounting more, so you would expect to have a much smaller noise, which means that you are going to have a very good quality, utility when you're reporting. And when the beta is very small, you're not going to discount much, and that means you're going to have a very large amount of noise added to the data, and that's almost as close as to the differential privacy. Not that we are discounting it still. So you're not getting exactly differential privacy, you're going to get very close to it as this amount of discounting goes to 0 and 0. And to conclude, what I wanted to present in this paper was just a view of how can we use discounting, which has been very popular in economics for good reasons, because of the way that we think about losses across time, in privacy. And those losses, now privacy losses, they are no longer financial, but at the same time, lots of those ways of thinking that might stem from self-control, or the fact that the data devalues over time, or the fact that we are setting aside financial the pot of money for answering the legal question that might arise from privacy infringes, would carry over nicely. And would have a nice interpretation when it comes to privacy as well. And this would allow us to have a differential privacy over an evolving data set that potentially the number of reports goes to infinity. So we are not restricted to a finite horizon, that we have to know in advance what the length of the horizon is. Now, we showed that you can achieve this privacy by using Laplace noise, and we observed that we can have even bounded noise when we are having exponentially discounted differential privacy, while this is not the case for the other notions of discounted differential privacy. And it remains to look into the optimal mechanisms in terms of the growth of the noise. Now, in the future work, it would be very nice to look into common adversaries that are out there. For instance, in the case of smart meter data, one adversary there, and one scenario there is essentially tracing attacks, that we try to look into aggregated consumptions and see if we can identify an individual household being in the part of that aggregate or not. Or non-intrusive load monitoring, when we look at the consumption of one house and we're trying to figure out what appliances were being used inside the house. Now, what will happen to the performance of the adversaries that are used in these contexts if we are using discounted differential privacy? Would we be able to balance the privacy needs of the people at the same time as having good utilities or not? So that would be a very interesting future work. And thank you very much for listening to this talk, and please do let me know if you have any questions or comments. Please feel free to email me or get in contact with me on Twitter. And also, please feel free to have a look at my webpage. There's the link to the paper and lots of other things there for you to download and look at. Thank you very much for your time.